All acids contain hydrogen. When that hydrogen is replaced by a metal, the compound that is formed is known as a salt. Magnesium sulfate is a salt. So is zinc chloride, so is potassium nitrate. So most of the examples that we discussed previously, which were formed as a part of neutralization reaction, were actually salts. Let's consider a few examples in table 17.1. The acid is hydrochloric acid, and it can form a sodium salt, which is sodium chloride. So most of the salts that come from hydrochloric, actually all of the salts that come from hydrochloric acid are chloride salts. So it's pretty easy. Nitric acid, whenever reacts with an alkali or with a base, would be able to form nitrates, such as potassium nitrate. Sulfuric acid would be able to form sulfate salts. Ethanoic acid would be able to form ethanoid salts like this one. This one is sodium ethanide. And phosphoric acid would be able to form phosphate salts like this one, potassium phosphate. Sulfuric acid can be thought, or all of these acids can be thought of as parent acids. Sulfuric acid is actually the parent acid of all the sulfates. So is hydrochloric acid for all the chlorides. The salts formed from sulfuric acids are all called sulfates. It doesn't matter if the replacement of hydrogen can't be done directly. For example, you can't make copper to sulfate from copper and dilute sulfuric acid because they don't react. So as we know this part from the metal reactivity chapter, we know that the reactivity of copper is too low to react with dilute sulfuric acid directly. There are, however, other ways of making it from sulfuric acid, such as we can take a copper to oxide solution, copper to oxide salt, and we can react it with sulfuric acid. It would still form a copper to sulfate, which is still a salt. So we have other ways of forming them, and we are going to discuss different ways of formation of salts in this chapter. Reminder, there are other salts that also contain ammonium ions. Salts that are formed when the hydrogen is present in acid is replaced by ammonium. We call them ammonium salts, such as ammonium chloride. Of course, that's when ammonia solution reacts with hydrochloric acid, it would form an ammonium chloride. And when ammonia solution reacts with sulfuric acid, it would form ammonium sulfate. So that's how it happens, that as soon as you look at the salt, the last name of the salt is going to tell you about the parent acid it was made from. So all chlorides are made from hydrochloric acid and sulfates from sulfuric acid. It's pretty easy to find. Reactions of acids. Before we look at some practical methods to make salts, we need to understand reactions of acids. Now, acid can react with metals. Remember, when acid reacted with a metal, it formed salt and hydrogen. This is something we've done with previously, but let's go through that. Metals below hydrogen in the reactivity series do not react with dilute acids. Metals above hydrogen in the series only react to produce hydrogen gas. They also produce a salt. The higher the metal in the reactivity series, the more vigorous the reaction with the acid is going to be. You will never mix metals such as sodium or potassium with acids because their reactions are way too violent. So it's easy to remember that metal plus acid forms salt plus hydrogen. The memorizing word is MASH, and this is a good way to memorize it. Now there are some reactions involving magnesium and acids. There is rapid fizzing, and a colorless gas is evolved, which pops with lighter splint, test for hydrogen, that is. So the reaction mixture becomes very warm as heat is produced. Magnesium gradually disappears to leave a colorless solution of magnesium sulfate. This is the reaction of magnesium with sulfuric acid, definitely forming a sulfate salt and producing hydrogen gas. This is a displacement reaction. The more reactive magnesium has displaced, the less reactive hydrogen out of its acid solution, forming the magnesium sulfate salt, and that gave hydrogen as a gas. All right. So this can work as an example to the MASH reaction above. Are we clear?
Yeah.
Okay.
Yeah.
So moving on, this is actually the effervescence or the bubbling produced during this reaction. With dilute hydrochloric acid, the reaction looks exactly the same. The only difference is that at this time, as we are reacting it with hydrochloric acid, a chloride salt would form, magnesium chloride to be exact. Now, in extension work, acids in solutions form ions. Dilute sulfuric acid contains hydrogen ions and sulfate ions. On the other hand, dilute hydrochloric acid contains hydrogen ions and chloride ions, just like we worked with it in the previous chapter. We can rewrite the equations above as ionic equations. In case of sulfuric acid, this can be written like this. Remember, I told you that we don't divide any solids, liquids, and gases into ions, only the aqueous solutions. So the acid has been divided into hydrogen ions and sulfate ions, as well as the soluble salt has been divided into magnesium ions and sulfate ions. If you cut the same ions on both sides, as this is the arrow sign, so we cut this ion with this ion, we're left with the ionic equation, which simply means that the magnesium, being more reactive, displaces the hydrogen ions. Then it is converted into magnesium ions in themselves and produce the hydrogen gas. The other reaction with hydrochloric acid and magnesium can be converted in the same way. Cut out the chloride ions, which are equal on both sides of the arrow. We're left with magnesium with hydrogen ions, which are then converted into magnesium ions plus hydrogen gas. So both the ionic equations are same no matter what the acid. The ionic equation looks the same because that's what happens in a displacement reaction. All solutions of acids contain hydrogen ions. This means any reactive metal, such as magnesium, will react with any simple dilute acid in the same way. And the same displacement reaction would occur, hence they would give the same set of ionic equations. Fair enough?
Yeah.
Now, this means that you can convert any displacement equation into its ionic equation like this one to this one, or by yourself. So what we usually ask our students is to practice different displacement equations, and we ask them to convert them into ionic equations by using the same method given over here. This is a pretty common question in IGCSE exams. Right? So let's move on. Reactions involving zinc and acids. Now, this is pretty much the same because just like magnesium, zinc is going to react. The only difference is zinc is lower down in the reactivity series than magnesium, so the reactions would be a little bit slower. So zinc plus sulfuric acid gives us zinc sulfate plus hydrogen, or zinc plus hydrochloric acid would give us zinc chloride plus hydrogen. And the ionic equations are going to be the same every time, because again, this is a displacement reaction. A more reactive metal is displacing the less reactive hydrogen ions from the acid solutions. So the ionic equation remains the same. Let's move on. Bases. We saw in chapter 16 that bases are substances that neutralize acids by combining with their hydrogen ions, and they produce water. When we are referring to the base at this level, we usually mean a metal oxide, a metal hydroxide, or ammonia. Now, reacting acids with bases, metal oxides such as copper oxide or magnesium oxides are bases. Reacting copper oxide with dilute sulfuric acid, just like I gave the example at the start of this chapter. Copper oxide is going to react with sulfuric acid. Copper oxide is actually a black powder. It reacts with dilute sulfuric acid, and it produces a blue solution of copper sulfate, and it produces water. All the metal oxide and acid combinations that you will meet at IGCSE level will behave in the same way as reaction between copper oxide and dilute sulfuric acid. They produce a salt and water. Most needed to be heated for the reaction to start. Copper oxide is an ionic compound which contains the oxide ion. It reacts with the hydrogen ions from the acid. They form water. So it's pretty easy that a metal oxide plus acid will give you salt and water. This is a neutralization reaction because the base neutralizes the acid and forms a neutral product, water, as we explained earlier in the previous chapter. So now some different bases in these reactions are, you can see sodium oxide. It's a metal oxide. It's soluble in water, And actually these two react to form the alkali, sodium hydroxide. All group 1 oxides do the same reaction. These are oxides. As soon as they are dissolved into water, then converted into hydroxides, they become alkalis. Most other metal oxides are not soluble in water. Group 1 are an exception. So calcium oxide is also likely to form calcium hydroxide like this. Another alkali we will see is the ammonia solution. Ammonia also reacts with water, form ammonium ions and hydroxide ions. All these solutions, sodium hydroxide, potassium hydroxide, calcium hydroxide, ammonium hydroxide, contain hydroxide ions. We call them alkalis as they are a source of hydroxide ions. Alkalis also can react with with acid and can form salt and water. Reacting acids and alkalis would be something like this. So metal hydroxides, which we are simply calling alkalis, can react with acid and can form salt and water. This is also a neutralization reaction. So an alkali reacts with an acid, forms a salt, and water. The ionic equation is like this. Mixing sodium hydroxide and dilute hydrochloric acid produces a colorless solution. So not much seems to have happened, but if you repeat the reaction with a thermometer in the beaker, the temperature rises several degrees, showing there has been a chemical change. Sodium hydrochloride solution is formed and neutral water is formed. Neutralization reaction for an acid reacting with alkali have the same ionic equation, this one, as I've explained in the previous chapter. They all involve hydroxide ions and hydrogen ions reacting to form water. And most of the neutralization reactions for strong acids and strong alkalis also involve the temperature rise. So this change is also going to happen with those. Keep that in mind because that has been important in past papers. Carbonate reacts with cold dilute acids to produce carbon dioxide. And this is the third category of reactions. The first category of reactions was metals and acids producing salt and hydrogen. The second category was acids or alkalis or acids and bases producing salt and water. So this is supposed to be the third category. A carbonate and an acid produce salt and water, plus it produces the carbon dioxide gas. Let's take an example. Copper carbonate with any acid, be it sulfuric acid, nitric acid, or hydrochloric acid, would form the respective salt because sulfuric acid would form a sulfate salt, nitric acid would form a nitrate salt, copper nitrate as you can see, or hydrochloric acid would form a chloride salt, copper chloride, copper 2 chloride actually, but they all form carbon dioxide and water. Carbon dioxide is a gas and produces bubble in this reaction just like we have over here. And carbon dioxide is then further added to lime water. It turns lime water milky, so we can recognize the gas by a simple test. The reaction between sodium carbonate and dilute acids is also going to give us a salt, carbon dioxide, and water. Now, if you try to write their ionic equation, you're simply going to cut the ions that are similar on both sides, which is actually sodium ions and the chloride ions. You'll end up with carbonate reacting with hydrogen ions, forming carbon dioxide and water. Right? This seems a little bit confusing. Let me explain why. Because in the previous chapter, when we were talking about carbonate ions, we were reacting them with hydrogen ions, and we produced a hydroxide ion, and we produced a hydrogen carbonate ion in the previous chapter. In this chapter, we're going with an equation differently. Let me tell you, these two can react together to form water and carbon dioxide further. That's why don't get confused. These are actually two steps. The final product, however, is water and carbon dioxide. So if you find the same reactants in the previous chapter with a different set of products, let me tell you that these set of products also react further to form water and carbon dioxide. So don't worry about the two reactions because this is just first half of the reaction. Actually, it settles down into carbon dioxide and water finally. All right. So don't let the reaction in the previous chapter confuse you.
Yeah. Okay.
Okay. So moving on, let's talk about salt preparations. We are going to talk about some practical methods going to produce salts, but salts can be divided into two kinds. Ones those are soluble in water and ones those are insoluble in water. Now, it depends which salt we need to make because they do have different methods to make. The soluble salts are made differently from the insoluble ones. So let's talk about the solubility of ionic compounds in water. When we discuss the solubility of ionic compounds in water, in order to bifurcate the soluble salts and the insoluble salts, there we have mostly all the positive ions that we usually discuss. Most of them come as metals from the reactivity series. There we have negative ions that usually come from most of the acids, such as nitrate comes from nitric acid, or chloride comes from hydrochloric acid, sulfate comes from sulfuric acid, carbonate comes from carbonic acid. However, hydroxide comes from the alkali, sodium hydroxide. If we talk about them, you would see that this table has been filled differently. Now, if there is nothing inside the cell, it's soluble. If it's completely brown, it's insoluble. But if there is a light color, it's almost insoluble or it's slightly soluble. Now take a look at this. You would find that calcium sulfate is very slightly soluble. So is silver sulfate, or so is calcium hydroxide. The rest, most of the salts are soluble. It's easy to decide this way. Let me explain how you can memorize this. All nitrates are soluble. Among chlorides, all of them are soluble except lead and silver. Among sulfates, all of them are soluble except barium, or calcium, which is slightly, or lead, which is completely insoluble, or silver, which is slightly soluble. Let me explain that all carbonates are insoluble except sodium, potassium, and ammonium. All hydroxides are also insoluble except ammonium, potassium, sodium, and barium hydroxide. Calcium hydroxide is slightly soluble. The rest of them are completely insoluble. So this is a good way to memorize them. Memorize them according to their columns. Don't try to memorize them according to their rows because that would make it a lot more difficult. You get the point?
Yeah. Okay.
Good, good. You're supposed to memorize this entire portion because this is going to help you decide which method you're going to choose for
So the
formation of
table
salt.
isn't given in the exam?
No, this one is not given in the exam. You're supposed to memorize it.
Okay.
All right. That's why I told you
Okay.
techniques of how to memorize it. Moving on. So these techniques are also mentioned over here. All sodium, potassium, ammonium salt compounds are soluble. All nitrates are soluble. Common chlorides are soluble except the two, so lead and silver. Common sulfates are soluble except the two, lead and uh, barium. However, silver sulfate or calcium sulfate are slightly soluble. Most common carbonates are insoluble. Only three of them are soluble: sodium, potassium, and ammonium, the ones we discussed above. And most metal hydroxides are insoluble. Potassium, sodium, and ammonium are soluble ones. Calcium is the only one which is slightly soluble. So all the techniques that I've discussed above are given in these sentences. Either memorize those techniques or these sentences, and it would be easier for you to memorize the whole thing. Right?
Okay. Yeah.
Moving on. So making soluble salts, except sodium, potassium, and ammonium salts, they all involve reacting a solid with an acid. For example, we can take acid with metal, but only for the moderately reactive metals. Remember, we have taken out sodium, potassium, and ammonium because we can react them with acid. The reaction would be too violent for us to handle in the lab. Or metal oxides or hydroxides with acids, or the carbonates with the acid. Whatever mixture you use, the method is basically the same. Let's go through the method. Measure 50 cubic centimeter of dilute acid into a paper and heat it on a tripod and gauze using a Bunsen burner. Now add a spatula full of your oxide. It can be copper oxide, it can be zinc, it can be any other oxide, metal oxide, except for sodium, potassium, and ammonium, of course. Continue heating. If all the copper oxide disappears, add more copper oxide. Keep adding more until there is some left in the beaker and it does not disappear anymore. Stir the mixture well to make sure that no more would react. At this stage, we have added excess of our oxide, and this is more than enough to react with the acid present, which means probably the oxide is left in the system. The acid has been completely neutralized. Why have we completely neutralized the acid? That is something important, which is explained in the second step. The second step is to filter off the excess copper oxide and transfer the filtrate, the solution, in an evaporating basin. Now, this easily explains why we have neutralized the acid completely. First off, filtration is usually done with a paper, and an acid can easily eat up the paper, so that's not the right way to do it. Secondly, the acid is usually soluble. If there was any amount of acid left, that would simply pass through the paper and come as a part of the evaporating basin. So the entire system of purification would be destroyed if we do not neutralize the entire amount of acid. So that's why it's important to neutralize the amount of acid and make sure none is present before the second step occurs. The solution we now have is simply copper sulfate, the salt and water. And the purpose of putting it into the evaporation basin is easy. Now we have the soluble salt and water. Heat the solution of copper sulfate over a Pearson burner, boil off some of the water, concentrate the solution, but make sure you do not evaporate all of the water. Keep heating until a saturated solution is formed. You can test this by dipping a glass rod into the solution. If the crystals form on the glass rod, when we remove it, we know that the solution is very close to saturated and the crystals will begin to form in the solution. And that's the point where we stop heating the mixture. We allow it to cool slowly at room temperature so that larger crystals can form. Remove the blue crystals from the reaction mixture by filtration or by just pouring off the remaining solution. The crystal can be dried by blotting them on a paper towel, or they can be left to dry in a warm place, maybe under the sun, maybe in a slightly heated up oven. Right? Now the question arises, why not simply evaporate the solution to dryness? This is something important. Now it seems much easier to just evaporate off all the water above boiling rather than crystallizing the solution slowly. But evaporating to dryness wouldn't give us the blue copper sulfate crystals. Instead, you would turn it into a white powder of anhydrous copper sulfate. Now that this is important that we explain this part. When many salts form their crystals, water from the solution becomes chemically bound up with the salt. This is known as water crystallization. A salt which contains water crystallization is said to be hydrated salt. Now, this shows the crystallization is a part of the reaction. Take a look at this salt. It reacted with water and formed a chemical compound that consists of a specific number of water molecules as a part of the chemical structure of the salt. Now this one has a specific color. Let me explain that this specific salt is white in color, and as soon as we added water, this was converted into blue. Now if you heat up this blue salt a lot, it can be converted back into this white salt. So that's why we never simply evaporate the solution to dryness. Because if we try to do so, we will convert this blue salt into a white one. So if we tend to evaporate the solution to dryness, we would always end up with the anhydrous salt, the salt without water. However, most of the time we want to get hydrated salts. So that's why we get to the point where we have a saturated solution, we do not evaporate to dryness, and then we simply dry them up. using a blotting paper. That way we will be able to get the blue salts we need. Fair enough?
Yeah, okay.
With eye protection, heating must be very gentle, avoid spitting of hot particles, and any non-serious action in lab. Safety comes first. Making magnesium sulfate crystals. You can add excess magnesium to sulfuric acid. This time the acid does not have to be heated. When we add the magnesium to the reaction mixture, it will fizz. Hydrogen would be given up. We keep adding magnesium until the fizzing stops. And there is some magnesium left in the beaker, but there is no acid left. All of the acid has reacted. This is the reaction. Again, the solution is concentrated by heating it and is allowed to crystallize. And this is the salt that we get. Remember, this is the hydrated salt, not the anhydrous one. However, this one is white in color. Now, how do you know whether you need to heat the mixture or not? Carbonates react with dilute acids in the cold, and so does magnesium. Most of the things that you're likely to come across need to be heated. So that's an easy way to know. Magnesium and carbonates can be used in cold system. However, all other substances, oxides or hydroxides or other substances, might need heating. So do the metals. Now, for sodium, potassium, and ammonium salt, there's a need of a different method. In this method, we've just been looking at you add an excess of solid to an acid and then filter off the unreacted solid. You do this to make sure all the acid is used up. This method does not work for making sodium, potassium, and ammonium salts. The problem is that all sodium, potassium, and ammonium compounds are soluble in water. The solid you add to the acid would not only react with the acid, but any excess would just dissolve in the water present. You wouldn't have any visible excess to filter off. There's no simple way of seeing when you have just added enough of the solid to neutralize the acid. Now, this solvent can be solved easily by doing a titration. You normally make these salts from sodium or potassium hydroxide ammonia solution, but you can use this, but you can also use the carbonates. Fortunately, the solutions of all these are alkaline, which means you can find out when you have a neutral solution by using an indicator. That's how the titration works. So the method of finding out exactly how much of two solutions you need them to neutralize each other is known as titration. You carry out the titration, you use an indicator, and that can tell you exactly how much acid is used or can be used to neutralize the exact amount of alkali. Once you find out how much of acid and alkali are needed, you can make a pure solution of the salt by mixing those same volumes again, but this time without the indicator. Remember, if you add the indicator, you won't have the pure solution of the salt. You'll get this mixture of solution of salt and solution of indicator because indicators are soluble. All right. So you're supposed to repeat the entire titration experiment, or simply you need to mix the volumes again, but without the indicator in order to get the pure salt. So making sodium sulfate crystals is an example of this salt. 25 cubic centimeter of sodium hydroxide solution is transferred to a conical flask. Use the pipette, few drops of methyl orange, get ready to do the titration, run the burette, and as soon as the color changes from yellow to orange, you know what amount of alkali acid you need to run or you need to use. The volume of acid needed is noted, and the same volumes of acids and alkalis are mixed together in a clean flask, this time without an indicator. This would be the reaction. We simply have the pure salt and water. The solution is heated to evaporate some of the water, again form a saturated system. As soon as you see the crystals, you can separate by filtration or pour away the remaining solution. The crystals are dried by patting them dry with a paper towel or leaving them in a warm place. And that's how we get our hydrated sodium sulfate salt. So the last part of this experiment after the titration is pretty much the same as the previous one, because you crystallize them and you dry them.